Okay, so we'll continue now looking at finite graphs. Okay, so again, let's ask the question about starting from some initial condition, does the epidemic survive forever? In this case, we know the answer to this. This can never happen. It's a finite state Markov process. It has an absorbing state, which is the empty set, and that's reachable from everywhere else. So eventually, you'll always hit that state. Okay, so in this case, extinction is certain. Okay, so it seems like this is uninteresting, right? So what's there to study in this model? It turns out that, in fact, there's something interesting that happens if you look at the time to extinction. Okay, so let's look at so start in some initial condition, and the one we'll typically consider here is you start with all the nodes initially infected, and then you look at how long it takes for the infection to disappear. So let's look at an example. So the vertex set is just n nodes. So this is going to be a finite subset of Z1. Okay, so that's our graph, the line on endpoints. And then, so let's define sigma of n to be the time to extinction starting with all vertices initially infected. So your initial condition is all vertices are infected. You look at the first time that you hit the empty set. Okay, so what's known about this? This was studied by Duret, Liu, and Schonman. And what they showed is the following. So if your infection rate lambda is smaller than lambda critical for Z1, for the infinite one-dimensional lattice, in this case, the lifetime of the epidemic scales logarithmically in n, the number of vertices in your finite segment. So here, sigma n over log n goes to some constant gamma 1, which depends on lambda. Okay, it has some interpretation, but we won't worry about that. And if lambda is bigger than lambda critical, then log sigma n over n goes to some other constant gamma 2 of lambda. So in the first case, your epidemic lifetime is logarithmic. And in the second case, it's exponential. So it's so sigma n goes to e to the n gamma 2. Okay, roughly. Okay, and both these convergences are in probability. These are random variables. Okay, so the second one's true. I'm not entirely sure what the mode of convergence is here.
I have to ask, but at rendezvous is polynomial.
Sorry, is?
At rendezvous is polynomial.
I don't remember that. At lambda c, I think there's a later result by Duret to that effect, but or by someone else to that effect, but I don't think that's in this paper. Yeah, then I think you're right that at lambda c it's polynomial. It's okay. Sorry, I misunderstood your question. So no. So you're not asking how does this behave at lambda minus lambda c at the exact value lambda equals lambda c. What's the epidemic lifetime? It's polynomial in one dimension, certainly. In d dimensions, I'm not sure. So Duret, Liu, and Schoenmann just showed this for one dimension, but the same result is true for finite subsets of the integer lattice. So if you look at the, so you have similar results for 1n to the d with lambda c of zd in the corresponding place there. I don't know if it's known whether the lifetime is polynomial at the critical value, but in one dimension it is. Okay, so this is the result for integer lattices. So are there versions of this also for other graphs? So what's known, for instance, on preferential attachment graphs? So this model was studied by Berger, Bogues, Chase, and Saberi, but before stating their results, maybe I should introduce this model briefly. Might be well known to several of you, but anyway. So this model was popularized, introduced and popularized, I guess, by Barabashi and Albert. And it's a model for network growth. You start out with some finite subgraph, say a triangle, and then you add nodes. And each node comes with some number of edges, m, and you are going to, and it's going to decide who to connect to with probability proportional to their degree. Or it might decide to connect randomly with some probability and with the remaining probability proportional to their degree. So let's say there are two edges it gets to assign. It might assign them to these two nodes. Along comes a new node. Now, this vertex has degree 2. This has vertex has degree 3. So the new vertex will have 50% more chance of connecting to the degree 3 vertex than to the degree 2 vertex. So that's the preferential and preferential attachment. So it might connect to these, etc. And you keep growing this. And what this growth model does, if you look at it at some large time and you ask what the degrees of the different vertices are, they are random, but what degree distribution do they have, then this growth model gives power law degree distributions. Okay, so if you let pk be the proportion of vertices with degree k, then pk is roughly some constant times k to the minus alpha. So in the original model of Barabashi, an Albert alpha was 3. There are ways of tuning the model to get different degree distributions, and everything we'll study will have degrees with power law bigger than 2, which is the minimum you need for a finite mean degree. Okay, so on this model, so contact process on this model. So this was studied by Berger, Forbes, and Saberi, 2005. And what they showed was the following. So the first observation is that lambda c equals 0 for this model for all alpha bigger than 2. So if you have, okay, so more precisely, what does this mean? For all lambda positive, you have, in the sense of, well, there's no critical lambda for this graph in the sense of the epidemic surviving forever. It's a finite graph still, so it has to die out. So we have to interpret what we mean by this threshold, and it's in this critical value, and it's in this sense that you have epidemics that live for exponentially long in the size of the graph. So for all lambda positive, the probability that the contact process lives for time bigger than exponential n to the gamma tends to 1. And here gamma is some positive constant. Okay, so there's some constant gamma that doesn't depend on lambda, such that the epidemic lifetime is always bigger than exponential n to the gamma. Okay, so that's a good question. Thanks. I should clarify that. So this is in the quench sense. So for almost every realization of the random graph, this is true. Yeah. Yeah, n is the number of vertices. Yes, n is. Yeah, so from now on, n is going to be the number of vertices in the finite graph. Okay, so this was their first result, and the second part of their result is, okay, so it also, they also characterize the metastable state. So you have a long-lived epidemic, and you can ask over this exponentially long time, is there some kind of pseudo-equilibrium? There's no real equilibrium, which is just the empty set, but is there some equilibrium distribution of how likely different nodes are to be infected? And they say something about this as well. So there's, for instance, that a fraction of all nodes are typically infected. So what do they show? Yeah, so what they show is the following. There exists some fixed constants B1, C1, B2, and C2, such that, so if you pick a vertex uniformly at random, and you ask whether this is infected during this metastable phase, then this probability is bounded as follows. So, okay, this is infected, okay, lies between so yeah, in this sense, there's a kind of polynomial dependence on lambda about how likely you are to be infected.
So you would also expect at the higher degree vertices would be, you would expect there to be strong correlations with degree.
Yes.
The probability that a random node of degree D is not infected should go exponentially down with D.
Yeah, I don't remember if they showed such results, but I agree that should be the intuition about what happens.
And to show that the extinction time grows exponentially with some power of n, does it suffice to consider a star around one of the higher degree vertices?
Exactly, that's what they do, and I'm going to talk about some results by others. Yeah, that's exactly what they do by looking at the high degree star. Okay, so these are the results they showed, and I should make one remark about this. So this result makes rigorous a claim of Pastor Sartoras and Vespiniani. That indeed the epidemic threshold is 0 for power law random graphs. With power law exponent alpha lying between 2 and 3. Okay. So they only claimed this result for this range of alpha, and this is the range of alpha in which the vertex degrees have infinite variance, and Okay, so and the size-biased degree distribution has infinite mean. So that was the intuition behind their claim. They used mean field methods. And they also claimed that this would not happen for alpha bigger than 3, that there you would have non-zero critical lambda. So their claim was in fact false for alpha bigger than 3. That was also shown by this result. Okay, so indeed mean field methods are not always accurate in this line of work. So this paper both made rigorous the claim in this range of alpha and showed that outside this range the claim is wrong. In fact, for all alpha you have the critical exponent is 0. Sorry, the critical infection rate is 0. Okay, so and can you say something about other kinds of finite graphs? So bounds for general graphs. So this is a paper of, that I had with Laurent Massoulier and Don Tousley. At the same time, around the same time as the paper of Berger, Bogues, Jason, Saberi, so this was independent work. We looked at a number of different graphs, including the power law graphs, so I'll go over the results in some detail. What we showed is for arbitrary finite graphs, some upper and lower bounds on the epidemic lifetime. And to state those, I need to introduce a couple of graph properties. So we have a graph G, and its spectral radius is defined as the largest eigenvalue of its adjacency matrix. Okay, so the adjacency matrix is the square matrix with the 1 if there's an edge between I and j. The ijth entry is 1 if there's an edge and 0 if there's no edge. So it's a symmetric positive non-negative matrix. So the eigenvalues are real and the biggest one in absolute value is positive by the Perron-Frobenius theorem. So that's the spectral radius. And the other quantity we'll need is its isoperimetric constant. So this is measuring the expansion properties of the graph. So you take the minimum over all subsets of the vertex set consisting of no more than half the vertices. You look at the cut. So you look at the number of edges crossing between this set S and its complement, and you divide by the number of vertices. So this ratio is the isoperimetric constant. And what are the results? The first one states that if your infection rate lambda times the spectral radius is smaller than 1, then the epidemic lifetime is logarithmic, and the mean epidemic lifetime so I'll use sigma n, the notation sigma n for the epidemic lifetime started with all vertices initially infected. This mean epidemic lifetime is bounded by some constant times log n. That's the main point. Okay. So you have logarithmic lifetimes. And if the infection rate times the isoperimetric constant is bigger than 1, then you have exponential lifetimes. The graph is finite. So n is the number of vertices. Okay, so you have different conditions for short and long-lived epidemics. The assumption is that the infection rate lambda is bigger than either smaller than 1 over the spectral radius or bigger than 1 over the isoperimetric constant. So in general, this doesn't imply any kind of threshold. In general, this doesn't imply a threshold. So the result of Duret, Liu, and Schoenmann showed that there's this sharp change from logarithmic to exponential, and we don't claim that, or we certainly don't show that in general that is true. Maybe it goes smoothly. But for those graphs for which the spectral radius and the isoperimetric constant are very nearly the same, okay, so if they are asymptotic to each other, then we do get a threshold. So this happens, so what are the graphs for which this happens? Well, it happens for Edrich-Remy graphs. So this is the random graph where there's an edge between every pair of vertices with probability p independent of everything else. So it happens here if p is much bigger than log n, if p grows faster than log n. So this condition basically says that all the degrees concentrate around their mean value. And so that mean degree is indeed both the spectral radius and is the isoperimetric constant. Log n by n, sorry. Yeah. Okay. So you are well inside the fully connected regime. And also this happens, and on random regular graphs, R is omega of 1. So if you have high degree random regular graphs, again, these two coincide with each other. They are very far away, yeah. Yeah, so for the line or for subsets of ZD for rectangles, the spectral radius is roughly the mean degree, and the isoperimetric constant goes to 0. So they are not expander graphs. So there is a gap between them. So results don't tell us much about or anything. And they also don't tell us much in this general form about power law random graphs. So that, yeah. It's always less than the spectral radius. So those two conditions are going the right way. Yeah, that's.
For constant degree, for expanders, it won't be tight, but it will be in the same degree.
Exactly. For expanders, these will be within a constant factor of each other. That doesn't, as n goes to infinity, they won't get further and further apart. So there, it's of some use, yes. There are bounds for it in terms of the second eigenvalue. So yeah, so if the spectral gap is big, then this is close in the sense of, I think, being within a constant factor of the spectral radius. Good question. Yeah, this may not be the correct thing to look at. So these were indeed motivated by the proof technique. So that's where they come from, not necessarily because they are the most natural thing to look at. So maybe I'll say a little bit about how the proof works as well. So just so you see where these two things come from. But before that, I'll say a bit more about the results. So again, we were also motivated by looking at power law graphs, and this particular approach doesn't tell us about them. So we had the same intuition about looking at high degree stars as a way of getting at the power law graph. So we have some additional results about the star graph. So you have a hub connected to n-1 leaves. In that case, what can we say? In that case, what we can say is that if the infection rate lambda is less than or equal to some constant over square root n for any fixed C positive, then the epidemic lifetime is logarithmic in the number of vertices. So you have quick extinction. And if you have lambda, which is a bit bigger than n to the minus half, so if it's n to the minus half plus some epsilon, then your epidemic lifetime is exponential. So it's omega the log of the expected lifetime is n to the epsilon, so the expected lifetime is e to the n to the epsilon. Okay, so this is for a star, and an immediate corollary of this is that if you look at a power law graph, then an epidemic on that survives at least as long as it survives on its highest degree star. So if you choose your lambda so that it's bigger than d max to the minus half plus epsilon with high probability. So d max itself is random. So if you choose it so that this happens with high probability, then again you have that the log expected lifetime is omega of d max to the epsilon, and on these power law graphs, the maximum degree is itself polynomial in n with some fractional power. So this is omega of n to the delta for some other delta. Okay. Yeah, for big enough infection rates. Yeah. So, okay, maybe just to compare with the results of Berger et al. So what they were looking at is, they said if lambda is strictly positive, not depending on n, then similar results are true. So we are looking at a range where lambda is much smaller than any constant, but is growing bigger than n to the minus half. Okay, so I'll just give a little bit of intuition about the proofs of these two results, about the general upper bound on the epidemic lifetime and the general lower bound. Okay, so there are two ways of thinking about the upper bound. One is to think in terms of, so we can dominate the contact process by what's called a branching random walk, where at each site, in the contact process, each site is either infected or healthy. In the branching random walk, each site carries some number of infected people, each of whom has a child at a neighboring site at rate equal to the infection rate lambda and dies at rate 1, and you can bound the epidemic process, the contact process, by that. And maybe an even easier intuition to think of it, it's exactly the same calculation, is that it's just a union bound. So you have some graph, and you have some initial vertices, and you want to know whether some vertex V is infected at time t. So you just, well, what needs to happen for that? You have to have some path along which infection traveled from an initial infected site U to V. And okay, that path might have, it doesn't have to be a self-avoiding path, so you could have gone, the infection might have gone U to W1, W2, maybe back here, W3, W4, and V is W6. So there's some path along which infection traveled from U to V, and then you find the probability of such an infection path and take the union bound over all paths. And that gives you exactly this bound. The reason the spectral radius turns up here is that if you take the union over all paths, well, how does the number of paths of different sizes grow? It grows like the spectral radius to the kth power for paths of length k. So that's where this comes from. For the proof in the opposite direction, so here we upper bounded the contact process. Here we lower bound the contact process, or the number of infected nodes. Well, the number of infected nodes itself isn't Markovian. You have to know where they are. But you can lower bound it by a Markov process. So if you're given some set of infected nodes here, so here are these two nodes which are infected. Where are they going to propagate infection? Well, they can propagate it from along every edge that goes out of this set to its complement. So if ST is the infected set at time t, Xi t was what we called it, Xi t is the infected set at time t, then number of edges from Xi t to its complement is bigger or equal to the isoperimetric constant times the cardinality of Xi t. That's the definition of the isoperimetric constant. So the total rate at which you are adding one more infected vertex is at least lambda times this. The rate at which you are decreasing the number of infected vertices is Xi t. So under that condition, precisely, you have a random walk with upward drift. The number of infected vertices is more likely to increase than to decrease. And we know that the random walk with upward drift takes exponentially long to hit the origin. And that's the idea. So that's where these quantities turn up. Okay, so that was the results about that paper. I'll come back again to more refined results about the contact process on power law random graphs, and this is a paper by Chatterjee and Durrett. Okay, so if you look at the results that Berger et al. Proved, or that we proved on the lifetime, on the epidemic lifetime on the power law random graph, what we showed was okay, so if you fix any positive lambda, then the epidemic lifetime, scales like n to some fractional power gamma that depends on lambda. This result was improved by Chatterjee and Durrett. And what they showed is that this is in fact very nearly exponential in n and not just in a fractional power of n. So they gave a better lower bound on the epidemic lifetime. Okay, and they also gave a better characterization of the metastable state, more detailed than was in the work of Berger et al. And better characterization. Okay, which I don't have the details of here. Okay, and what did they do differently that helped them get these better results? So they were more careful in looking at, so the intuition was still to think about the power law graph in terms of its high degree stars. But whereas what both we and Berger et al. Did was just to pick the highest degree star, they looked at the interaction between different stars, that if you have epidemics which are so long-lived, it can pass from one high-degree star to another, and that can help it live even longer and so on. So taking those interactions into account helped them sharpen a lot of the results. Okay, so that's what I wanted to say about the contact process itself. I have about 10 more minutes. Yeah.
So is that trivial upper bound to the n upper bound of the
For positive lambda, I don't know of any. I guess so. It's a good question. No, I would be surprised if that was the case, but I don't think the focus has been more on proving lower bounds, and I don't think there's been work on proving upper bounds in that setting.
The average degree is constant. It can't be more than exponential. Everybody recover before there's a single infection anywhere in the graph. Probability of that in a given period of time would be
Exponentially small. Yeah. Okay. Yeah. Yeah. Good point. So it can't be more than exponential in the number of edges in the graph.
Before you move on, I wanted to ask a question about this claim by Pastor Sartorius and Vespiniani.
Mm-hmm.
So, knowing a little bit about what they probably did, even though I don't know that paper, they probably showed that the fraction of infected individuals is tending to zero in some sense, even though the epidemic doesn't completely go extinct.
But even that would be incorrect. I think.
That's also.
Yeah. So even the fraction shouldn't go to zero by the results of Berger et al.
I guess more generally, it seems like there, in some families of graphs, you can imagine an additional threshold question about when asymptotically the disease becomes rare, because when it disappears.
Yeah.
Maybe it's still surviving, but only on a small handful of high-degree vertices.
Yeah, that's a good question. There must, yeah, because if it survives on the star and its immediate neighborhood, that's still a vanishing fraction of the total number of vertices. So is there some regime where it only survives on those? Yeah, that's, I don't know the answer to that. It might be very close to the threshold that happens. Okay, so I have only 10 more minutes. So maybe I'll just talk about a couple of interesting models that are a bit different from what we have looked at so far, but there are some interesting results about them, and they are motivated by applications. So they are not contact processes. So I'll use the word epidemic to mean something quite different. So we'll call them competing epidemics. What they are, in fact, is competing first passage percolation. So you have, so the motivation, I should have talked about motivation a long time ago, but why are we studying epidemics? Apart from the obvious biological motivation, there are lots of others that computer scientists are interested in, and people in other disciplines. So one is malware in computer networks, which is very similar, but it's also a model for the spread of opinions, spread of ideas, contagion, financial contagion, spread of faults, etc. So if you're thinking of spread of opinions, or if you're thinking of applications in marketing, then you may have two or more products competing, and you want to make sure that your product gets to most of the consumers, let's say. And so what we have here is the model is the following. Okay, so there are a few papers, so models. So you have a competition between two colors. Spreading from two initial source vertices. And once a vertex acquires a color, it keeps that color forever. It won't change to the other color, and it won't lose its color. So. Okay, so this is really not a model of epidemics, but of first passage percolation. So you're asking which color do you acquire first? And the question is, so what fraction of vertices, or how many vertices get each of these colors? So let me state some more precise models first, so we can pose the question more formally and then say something about them. So we are going to study these questions on the random graph model, on the following random graph model. Which is the configuration model with power law degree distribution. So same as before, pk, so the proportion of, the probability that a vertex has degree k is roughly some constant times k to the minus alpha. The configuration model again may be familiar, but if not, it's quite easy to describe. So what you do is, for the first thing you do is you have your n vertices. To each of them, you independently draw a degree from this degree distribution, and you assign that many half edges. So you might pick a degree 2 for this, 3 here, maybe 3 again here, 4, 1, and 3. And then you just match up these half edges at random. So you might match these two. So you match them up at random in some way. And this this matching could create multiple edges, and it could create self-loops, okay? So for each vertex, pick a degree at random. dv at random, and create dv half edges. And then match these uniformly at random. Okay, and you can decide to keep this, in which case you may not get a proper graph, or you can decide that if you don't get a proper graph, you throw it away and start again and keep doing it till you get a valid graph. So that's the configuration model. It's one specific model of a random graph with power law degree distribution. So a half edge is like an edge connects two vertices. Now I'm not creating edges at first, I'm creating stubs. So I decide I want to have 5 friends. I create 5 half edges that can potentially be friends, and everybody else does this. And then we just match up at random, and whoever matches, matches my half edges, those are my friends. And 2 of them might might match up with half edges of the same person, in which case I have the same friend twice. But if you don't want to allow that, then you keep repeating this process till we get a proper graph. I could even match up my own half edge, so I'm my own friend. So you could have that too. What's the matching? There's uniformly at random, that's all. So you have this big bag of things, the straightforward algorithm. So you could ask, how do you achieve uniformly at random? But that's easy. So you pick, you order them any way you like. You pick the first half edge, pick another one from all the free, still available ones uniformly at random, match it up, throw them away, and repeat the process. That achieves a uniform matching. If this model seems a bit unclear, there's something else called the soft configuration model, which achieves almost the same. It's also called the expected degree model. So now here each vertex acquires a weight according to the degree distribution, and then you put an edge between any pair of nodes with probability proportional to the product of their weights. So these models are very similar to each other. It's just that if you do a proof for one model, it's not immediately obvious it applies to an equivalent model. And this is the model they studied in their paper. So I thought it's worth saying that. And also you'll see the configuration model a lot when studying, when reading papers on this topic. So it's useful to know what the configuration model is. Okay, so there are a few different papers on this, of which, okay, so let me state the problem, and I'll overrun by about 5 minutes if that's okay. Okay, so now we pick two vertices R0 and B0 uniformly at random. Okay, so R0 is going to be colored red, B0 is blue, and then the color is going to spread out from these. So there are two models. There's the fixed speed model. So in the fixed speed model, there's a constant, it takes constant time for a color to cross an edge. So red takes 1 time unit to cross an edge, and blue takes some deterministic lambda bigger than 1 time unit to cross an edge. And then there's the random speed. Red takes x1 time, IID across edges, and blue takes exponential, let's say 1 over lambda to get the same mean. And this is again IID and independent of red. So these are two models. Okay, so what do you think is going to happen?
In the fixed speed model, if a node gets both red and blue at the same time, do we have to?
Good question. So in the fixed speed model, you do have to say something about what happens. So let's agree on some tie-breaking rule, probability half, that you give it either color when that happens. That's in the random speed. That the fixed speed is deterministic. Everything's deterministic except the realization of the graph and where the nodes are initially placed. So once the graph is given and your initial points are given, everything's deterministic after that. Yeah. Okay. Okay, so what would you expect? Are they each going to get a proportion? Is one going to get most of them? One's going to get most of them. That's what you think, and that's true. Okay. So result for fixed speed. Okay. Okay. Most vertices become red. And then you can say quite precisely, okay, And these results are all for most realizations of the graph. Fraction tending to 1 as n goes to infinity. Most vertices become red, which is faster. Okay, and with high probability, the number of blue vertices is exponential of log n to the 2 over lambda plus 1 times some random variable. So there's some randomness, but the scaling is the number of blue vertices is really tiny. It's not even n to a fractional power. It's even smaller than that. Okay. This is for, this is for any alpha between 2 and 3. I don't know if I said it there. So this is for alpha between 2 and 3. Yeah, if there's any dependence, it's just in this bit. The scaling is the same for all of them. Okay, and this result was due to Baroni, van der Hofstadt, and Congaty. I think that case is more delicate. I don't know if that's been studied. There it might be. If they have the same speed, then it's possible that even the initial randomness makes it winner takes all, but I don't know what the result is in that case. Sorry, Exactly. So the analysis is looking at how quickly do you get to the high degree vertices. Yeah, and if one of them's closer, that will help it dominate. Yes. Okay, so that's in the fixed speed case. So what do you expect is going to happen with random speeds? Again, alpha is still between 2 and 3. Is it going to become a bit fairer or a bit more unfair? Okay, something interesting happens. So most vertices become the same color. But which color it becomes is random. Okay, so the faster one is not guaranteed to win here. So the probability that wins is the probability probability that V1 is smaller than lambda V2, where 1 V2 IID with some specific distribution. Okay. don't care what it is, but there's some random variable. So you take two realizations of the random variable. So the faster one has a bigger chance of winning, but still it's random who wins. So in that sense, it's a bit fairer, but in terms of how much the winner gets, the winner takes all in an even stronger sense here. So, but winner takes most of the nodes. So the losing color gets only order 1 nodes. Okay, or number of nodes. The losing color converges to some in distribution to some limiting random variable n loser. Converges in distribution. So this is some fixed random variable not depending on n. So the losing color gets only order 1 vertices here. Yeah, yeah. Yeah, but you somehow think you're picking these lots of times. So somehow, as you pick more and more of these, things might average out, but it's not happening. And the intuition behind this is that this is a branching process. The number of vertices of each color, till they start meeting each other, they are evolving independently. They are branching processes looking at your neighborhood. The branching process has offspring distribution, which is the size bias distribution. So you have your degree distribution has infinite variance. The size bias distribution has infinite mean. So this is an explosive branching process, meaning that at some finite random time, it becomes infinite. So whichever of these two colors hits infinity first wins and takes all the vertices. And that's the idea. And this result was Deifen and van der Hofstad. Okay, and both these are 2015, I think. Okay, I think I'm well over time, so that's a good time to stop. I think it would get a lot harder when you get to that point. So that would really be the competing epidemics case, I guess, rather than competing first passage percolation, and that would be a lot harder. I don't think anything is known about those. So what if you relax the condition that once you acquire a color, you keep it forever? Maybe you lose your color after some time, and then somebody else can color you.
There are also these models that talk about threshold adoption, that is, you adopt a color after you see a certain number of colors and so on. Any of this help in analyzing those?
So the simplest version of that model is what's called bootstrap percolation. So there you have to have, there's some fixed threshold R, not a variable one. So you need at least R neighbors to become infected before you become infected. And there are some very nice results for that by Jansson with various co-authors. Jansson, Lukchak, Turova and Veye. So they look at this on their de Cheney graph, and what they show is that there are sharp thresholds. So you have to, if you start with too few initial infected nodes, and this will be, on n nodes, it will be n to some fractional power, depending on your threshold R. So if you start with too few, you don't grow much at all. Your final infected set is your initial plus a tiny bit more. And if you start with just a little bit more than that, most of the n nodes, certainly a fraction going to 1, get infected. The number left is, I think, still a fractional power of n. So there's a very nice sharp threshold for that. Yeah, I didn't read those papers. There are results on that, so I don't know. But it's Perez and co-authors have looked at that. I didn't define it very precisely, but if you have somehow your process is living for exponential n time, let's say. So pick some large time, exponential square root n, something like that, which is still far from extinction. And then ask, what is the distribution at this random time? Sorry, what's the distribution at this time? That's a metastable distribution. You've had long enough to equilibrate, but you're not so close to the end that you're picking that up.